So let us start. So yesterday I discussed Serre-Frenet formulas on a space curve r equal to Rs. So this is our regular curve, and on this regular curve we have a set of triplets. In fact, these are 3 unit normal vectors, orthonormal vectors. The first one t is the unit tangent to the curve, and n is called the principal normal, and b is called the binormal. So this is the Frenet trihedron. For the curve C. Now what we do, we consider that they are derivatives. So the derivative of t with respect to s, denoted by t dash, is given by kn, where k is the curvature of the curve, and the second equation was dn over ds, denoted as n dash. It is minus times tau n, no, tau b minus kt, tau b minus kt, and the derivative of b, denoted by b dash, is minus tau n. So this is the set of formulas known as Serre-Frenet formulas. Now what I will be doing today, I will look at some of the applications of these formulas. So this first of all will help us in finding higher order derivative of r in terms of the curvature k and torsion tau of the curve. So we have the curve r equal to Rs. The first derivative of r, that is r dash, is in fact the unit tangent t. The second order derivative of r with respect to s, of course, is t dash, which is kn by Serre-Frenet formula. And the third order derivative of r, this you can write down as r triple dash, is in fact, now I have to write down the derivative of kn. So k is also function of s, so that is k dash into n plus k into n dash, and this is k dash n plus k into n dash is available to us. It is tau b minus kt. So tau b minus kt. I can write it down more simply as minus k square t plus k dash n and plus k tau b. So this is the third order derivative of r. So this is the first order derivative, call it 1, second order derivative, call formula number 2, third order derivative is formula 3. You can go on computing it, and let me compute one more derivative, that the fourth order derivative of r. So I have to differentiate formula number 3 with respect to s. So that will be minus times 2k into k dash t plus or minus k square as it is into t dash plus, now over here k double dash into n plus k dash into n dash. N dash is tau b minus kt. Okay. The last term is k tau b. So, derivative of k tau is k dash tau plus k tau dash into b plus k tau into b dash. B dash is minus tau n. So, this plus will become minus, this will become square into n. Now, let us collect the terms, similar terms. So, this is the term of t and this is the term of t. These are the only two terms of t. T dash also you can write down as yes, this I can replace by k n. So, that will become k cube n and minus sign also. Minus sign? No, it will remain minus in fact. Okay. Any other thing? Okay. Now, let us collect the similar terms. So, terms of t are only 2. So, that is 2 k k dash t and minus k k dash t means minus 3 k k dash t. Now, search the terms of n here, here. So, here, here and the last one. These are the 3 terms of n. So, plus I will write down this first. So, k double dash and minus k cube and then minus k tau square into n. Okay. And now, we have to look at the terms of b. So, this is the term of b and these are the 2 terms of b and that is all. Okay. So, you will be having k dash tau means 2 times k dash tau. Okay. And then plus. Okay. All terms are positive. So, plus k tau dash into b. Okay. So, this is the 4th order derivative of r. This is number 4. You can go on differentiating r again and again up to order n. What you will notice all the time that the coefficients of t and n and b will always be terms involving k, tau and their derivatives, and every time the derivative will be linear combination of t, n and b with coefficients as functions of k and tau. This is the observation that we have on differentiating r n times. So, this I computed only for this observation. Okay, this is an important observation. And now, these formulas help us in obtaining many other important relations. I have got some problems so that you can use these things. All right. So, this is one of an example or rather it was an exercise. Show that the scalar triple product of r double dash, r triple dash and the 4th order derivative of r is k to the power 5 into d by ds of tau upon k. And in solving this problem, you will notice that how we will be able to use these formulas in obtaining these crisp relations involving curvature and torsion. So, these derivatives are available to me here. I will just compute this scalar triple product. So, first of all, I will write down the left hand side as r double dash cross r triple dash and this vector dot with r 4 dash. Okay. So, this is the left hand side. Okay. So, this is the left hand side, and now let me compute it first. So, r double dash cross r triple dash I can compute as a determinant. Now, my frame is the frame who's generated by T, N and B. So, instead of writing I, J, K, we will write down T, N and B. So, here I will be writing T, N and B. The component of R double dash such here it is K N. So, this is 0, K 0. Okay. R triple dash is here, component of K is minus K square, component of N is K dash and component of B is K tau. So, this is the cross product of R double dash and R triple dash, and this can be written as this is K square tau into T, and then minus times 0. Component of N will be 0. So, you leave it here, and then plus what are the components of B? 0, and then it will be K cube into B. Okay. Okay. So, this is R double dash cross R triple dash. Okay. And next I have to find the dot product of this vector with fourth order derivative. So, next R double dash cross R triple dash and dot R fourth order derivative. This is a scalar triple product of R double dash, R triple dash, R 4 dash. Okay. So, let us do it. Okay. So, I can look at these two vectors, one is this, other one is written here. So, K square tau is to be multiplied by minus 3 K K dash. So, K square, so this will be minus 3 K cube into K dash into tau. Okay. This is the dot product of T component, and N component is missing here. So, that is 0. B component is this, and here it is K cube. So, this will become plus 2 K cube into K dash tau plus K to the power 4 into tau dash. Okay. Is it okay? Yes, dash was missing. 3 K K dash is to be multiplied by K square tau. So, K cube into tau into K dash, that is right. Now, everything is fine. Okay. So, these two terms can be combined, they are same in fact. So, this becomes minus times k cube into k dash tau, okay, plus k to the power 4 into tau dash. Okay. Now, I can take k to the power 3 common. So, k cube is common. What you get is k into tau dash and minus k dash tau. Okay. Now, this bracket suggests that I should multiply and divide by k square. Okay. So, this term in the bracket you can see is the derivative of tau upon k. So, this k square and k cube will become k to the power 5, and this quantity is derivative of tau upon k. And this proves our assertion that the scalar triple product of these three vector is actually k to the power 5 into d by ds of tau upon k. Okay. So, I was able to make use of these relations in solving these problems. Okay. Yes. Now, there is another problem about the general helix. So, a helix, we most of the time in discussing example we consider circular helix, but more generally circular helix but defined through a property. So, let me write down the definition of a general helix. A helix, so this is the definition. A helix is a space curve which is characterized by the property that this property I will put under inverted commas, that tangent at any point, the tangent at any point of the curve makes a constant angle with a fixed line. This is the property of the curve which characterizes the helix, and characterization is as good as the definition. So, we take it as a definition, and this fixed line is called the axis of the helix. The fixed line in this case, the fixed line in this case is called the axis of the helix. All right. So, this we will be assuming as the definition of the helix. Okay. Now, in terms of curvature and torsion, that can be defined. So, this is a problem. Show that show that a necessary and sufficient condition necessary and sufficient condition for a curve to be a helix is that the ratio of its curvature and torsion is constant. So, this is yet another important property of the helix. In fact, once again a characterizing property, that the ratio of curvature and torsion will remain same at every point. Okay, so, this can be solved, solution of the problem. So, what I will do, I will choose a unit vector along the helix, along the axis of the helix. So, let us see with this equation be a helix. Okay. Then what we do, we choose a unit vector. So, choose a unit vector A along its axis. So, A is a unit vector along the axis of the helix, and if T is a unit tangent, then I can compute the angle between them. Then A dot T will be what? It will be modulus of A into modulus of T into cos alpha. Modulus of A is 1 because it is a unit vector. This is also a unit tangent. So, right side will be simply cos alpha, where alpha is the angle between A and T. And what is said in the definition, that this angle remains the constant. Tangent at every point makes a constant angle with the axis. So, the right side becomes constant. This is a constant by definition. Here alpha is the angle between A and T, and this is constant by definition. Okay. I can rub off this part. Okay. Now, what I will do, I will differentiate this. Okay. If you differentiate it, okay. So, differentiating this, in fact, A can be written as okay. We can write A, can we? We can write down A as A equal to, okay, we can write down, no, just without writing. Okay, I am sorry. what you do is you differentiate a dot t equal to constant. So, differentiating the above, differentiating the above relation with respect to S, of course. So, A is a fixed vector. So, A dot t dash, that will be the derivative in the left hand side. Right side is constant. So, derivative will give you 0. So, what do you get from here? That A t dash is k n. I had just written down Serre-Frenet formula. So, this is k times A dot n equal to 0. Okay. So, k is non-zero. So, A dot n is 0, which means A is perpendicular to n. And once A is a unit vector perpendicular to n, it lies in the plane of t and b. So, this implies A lies in the plane of t and b. Okay. So, I can write down A as a linear combination of t and b, and one of the component, when you will express it, it will have coefficient along t and coefficient along b. So, coefficient along t is already known to us. So, A must be equal to cos alpha into t. Since a unit vector, one of the coefficient is cos alpha, the other must be sin alpha. So, this relation has helped me to write down expression for A. Okay. So, A is selected. Okay. All right. Now, differentiate this once again. So, differentiating this vector with respect to S. So, differentiating with respect to S implies what you will be getting. Left hand side will be 0 because it is a constant vector, it is a fixed vector, and the right side cos alpha is fixed, derivative of t, let me call it t dash, plus sin alpha is constant, so b dash. So, 0 is equal to cos alpha t dash by Serre-Frenet formula is k n. So, k times n plus sin alpha into b dash is minus tau n. So, minus tau sin alpha into n. Okay. Now, or I can say that 0 equal to, this 0 is a 0 vector in fact. So, this is k cos alpha minus tau sin alpha multiplied by vector n is a 0 vector. Now, a scalar time a vector equal to a 0 vector means, and this is a non-zero vector, it is an element of Frenet triadan. So, the scalar must be 0. So, this implies k cos alpha minus tau sin alpha equal to 0, which is equivalent to saying that k upon tau equal to 10 alpha. Alpha you have assumed to be a constant because of the definition, and therefore, the right side is constant. So, you have proved that for a helix the ratio of curvature and torsion is a constant. So, we started with the assumption that we are given a helix and we proved that k upon tau is constant. Now, the converse of the statement is also true. So, in the converse part you start with this assumption that for a curve k upon tau is constant, and show that this constant this curve is a helix. So, this argument that I gave you were reversible argument. You can go the other way around to prove that it is a yes, a dot t equal to constant, which is equivalent to saying that the angle between the tangent and a unit vector along axis is constant, and by definition it will become a helix. So, the converse is obviously true, and you can prove it by going the other way around. Converse can be proved by proceeding in the reverse direction. Okay. So, this proves the statement from both sides. Okay, now. So, now this brings us to the fundamental theorem of space curve. How much time I have spent?